In the previous episode, the transport block was divided into multiple code blocks. Each code block is now ready for channel coding. But why do we need channel coding? Why not simply transmit the original bits through the wireless channel? Because wireless channel introduces errors through noise interference and fading. Before transmission, the data must be protected. The first step is LDPC encoding. Instead of changing the original information, the encoder computes additional parity bits. These parity bits are generated from the information bits. And later, they help the receiver detect and correct transmission errors. Finally, the original information bits and the newly generated parity bits come together to form an encoded code block. The encoded code block now contains the original information, plus extra redundancy, to make wireless communication more reliable. Suppose a few bits are corrupted during transmission. Without channel coding, the receiver simply receives incorrect data. With LDPC, additional parity information gives the receiver the ability to detect and repair many transmission errors. After LDPC encoding, we obtain a long stream of encoded bits. However, every transmission is allocated a different number of resource elements. Sometimes, only a few are available. And sometimes, many are available. Rate matching adapts the encoded bits, so they exactly fit the available radio resources, whether we have a small allocation or a large one. The encoder produces an output of 16 bits. Suppose the scheduler allocates space for 24 bits. But the encoder produced only 16 bits. Rate matching repeats selected bits. But now, only 10 bits can be transmitted. So rate matching removes selected bits through puncturing. Whether bits are repeated or punctured, the objective is always the same. Produce exactly the number of bits that fit into the allocated PDSCH resources. Even after rate matching, the bit stream may still contain long runs of zeros or ones. And these predictable patterns are undesirable for radio transmission. The scrambler combines the data with a pseudo-random sequence, making the transmitted bits appear random. The information remains exactly the same. But the transmitted sequence now has much better statistical properties. The result has better spectral properties for radio transmission. The scrambler combines the encoded bits with a pseudo-random sequence using a simple XOR operation. The resulting sequence may look completely random, but the information is still intact. At the receiver, the same pseudo-random sequence is generated, allowing the original encoded bits to be recovered. Let's quickly review the complete PDSCH processing chain. First, a cyclic redundancy check is attached. Large transport blocks are segmented into multiple code blocks. Each code block is independently protected using LDPC encoding. Rate matching adjusts the number of bits according to the available radio resources. Finally, the encoded bits are scrambled to randomize the transmitted sequence. The processed bits are now ready for modulation and resource grid mapping. So far, everything has been just zeros and ones. But here's the problem. Radio waves cannot transmit bits directly. Instead, groups of bits are mapped to symbols, each represented by a specific point in the constellation. But how exactly does each bit pattern become a constellation point? That's where modulation comes in. And that journey begins in the next episode.